What I want you to do now is something slightly more theoretical, and that is to look at the case when we have only a dependent source. Now, this is a little bit of an unusual case. Doesn't happen very often, but it can. So let me just quickly show you. Here's a possible circuit that we're going to work. Now, dependent sources require special consideration. First of all, there's no independent source in this problem, so there's no way to determine Vx. In this problem, we would end up with Vx as an undetermined variable. So in order to find our Thevenin equivalent, we have to use kind of a special technique. So what we're trying to get to is we want a circuit that looks like this. And in the past, we've done that by finding the open circuit voltage and the short circuit current. But because if we only have a dependent source, we don't have anything powering the dependent source, so we can't actually find an open circuit voltage and a short circuit current. So what we do then is we take another approach and we say, okay, I'm going to put a little voltage source here and I'm going to call it V-test. And I'm going to say that the presence of that voltage source will generate a current I-test. And then I'm going to find the Thevenin. I'm going to write a KVL around here and look at the relationship. So I have minus V Thevenin plus I-test R Thevenin plus V-test is equal to 0. So V Thevenin is I-test R Thevenin plus V-test. Now remember, the whole concept of a Thevenin equivalent circuit is that the circuit will be equivalent no matter what is attached to terminals A and B. The voltage and the current at terminal A and B will have to be the same for the Thevenin equivalent as well as for our circuit that we're trying to find the Thevenin for. So I want you to keep this equation in mind. We'll come back to it. And what I want to do is now come and look at this circuit, and we'll clean this slide up a little bit. Let's shrink this guy a little and move him up here. So given this, what we're going to want to do is we're going to want a way to find the Thevenin equivalent circuit. It's got only a dependent source, so what we're going to have to do is we're going to have to come in here and put our test voltage source and our test current. Let's come back. We want to do it exactly the same way we did this one. Notice our test current was pointing down, so we'll do that here. And as long as I do that and I define V-test and I-test in exactly the same way, then I can use this equation that I derived, which is V Thevenin is going to equal I-test R Thevenin plus V-test. Let's go back and confirm that. Yes. All right, so what I want to do then is I want to start writing a set of equations, and in this case, node voltage looks pretty easy. So I'll work with node voltage. I could do mesh current, but then I would have to write a super mesh, so I think I'm going to work with node voltage. So let me call this node here V2, and let me call this node V1, and let me ground, put a reference here at the bottom. And before we do much more, let's just note that V-test, my test voltage, is going to equal V2, my node voltage. Vx, my dependent source variable, is V1 over it's V1, actually. It's equal to V1. So V-test is equal to V1. I'm sorry, Vx. Vx. So that's a substitution here that I can use. All right, so writing each node equation, and I am going to have to write two. I'll have V1 over 10 plus V1 minus V2 over 20 is equal to 0. And then at node 2, I'll have V2 minus V1 over 20 plus V2 over 30. Oh, wait. Let's go back and note a couple of things. So I don't want to impart any confusion. So I already have my node 2 voltage defined. So normally, if this were a node voltage problem and we knew the value of V test, this would be a sufficient set of equations. But we actually don't know the value of V test, but that's okay. So V1 is Vx and V2 is V test. So let's substitute V1 over 10 plus V1 minus V2 V test over 20 is equal to 0. Okay, and then V1 is Vx, but we're not really using that yet. Okay, so I don't have enough equations. So what I eventually want to do is I want to get an equation where the only unknowns are I test and V test, so that I can put it in this form and I'll read directly from the equation V Thevenin and I Thevenin. So what that means is I need to go ahead and write a node equation at V2. Even though V2 is defined as V test, I need that node equation because it will have I test show up. So I test is defined. I'm going to treat it like an unknown in my node equation. So now it's time for me to write that node equation. I was going to write earlier. V1 minus V2 minus V1 over 20 minus Vx over 6. And then so that's entering the node, plus V2 over 30. And then I have I test leaving the node. I'll just put that in as a current. Okay, so I've got this one. And I've got this one. And I've got this one. So first, let me substitute V1 for Vx. So V2 minus V1 over 20 minus V1 over 6 plus V2 over 30 plus I test is equal to 0. Now, if I come down to this equation, and also V2 is V test, so let me do that. And let me also multiply through by 60. So V test minus V1 times 3 minus V1 times 10 plus 2 V test plus I test is equal to 0. And I'm really hoping I'm not making an algebra error here. Okay, from this equation, I get that 2V1 plus V1 minus V test is equal to 0. So 3V1 is equal to V test. I think that's right. Let's see, 2 and 1. Yes, so V test is, or V1 is V test over 3. So I should be able to substitute that for V1. So I have 3V test minus 3V test over 3 minus 10V test over 3 plus 2V test plus I test equals 0. And now I've accomplished what I want to accomplish in that I have only V test and I test as unknowns. So playing around with that, that's 2v test minus 3.3 v test plus 2 v test plus I test equals 0. So combining some terms, that should be 0.6 v test plus I test is equal to 0, assuming I didn't make any math errors. So given that, we have relating that to this equation and drawing a one-to-one correspondence, I need to rearrange so that v-test does not have a coefficient. So I think that means v-test is roughly 1.5, or v-test plus roughly 1.5 I-test. That's not quite right, but you can get the numbers if you work through this example on your own. So now drawing a one-to-one correspondence here, this 0 is occupying the position of V Thevenin. So V Thevenin is 0, R Thevenin is 1.5. So what does that mean? It means for that dependent only source, you basically just have a resistor. So the Thevenin equivalent voltage when you have only a dependent source is 0, and a dependent source will give you a Thevenin equivalent resistance. The reason that the unknowns were chosen to remain unknowns, and I didn't put a specific number here, is so that you can track those through and see how that works. Now this method will work for any circuit, dependent sources, independent sources, any circuit. It's the most complicated of the methods, so we tend to reserve it for the circuits that only have dependent sources, but it would actually work for any of the previous problems. It is the most general approach to put a test source, show a test current, and figure out then what direction things flow. Interestingly enough, it is possible in these circuits when you have only a dependent source present to get a negative resistance. All that means is it just has some implications for whether the dependent source will produce or absorb power and how that works in the circuit. If you get a negative resistance, that's unusual. It probably also has something to do with perhaps you defined your equation or your source directions in a more in a different way. So anyway, that is how to find the Thevenin equivalence